Welcome. Today we're diving into an invisible force, a force that connects something as simple as a kitchen knife to something as huge and powerful as a cyclone. Sounds crazy, right? Well, let's find out how it all works.
Okay, let's start with a puzzle you've definitely seen in your own kitchen. You grab a knife, right? If it's blunt, you can push and you kind of just smush whatever you're trying to cut. But then you grab a sharp knife, use the exact same push, and it glides right through. So what's the deal? What's the secret?
The secret isn't really about how hard you're pushing. It's all about where that push is going. With a blunt knife, your force gets spread out across a wide, dull edge. But with a sharp one, that very same force gets packed into one super tiny point. It's like using a laser instead of a floodlight. All your energy is focused on one single spot.
And that whole idea of concentrated force, well, that brings us right to our big topic for today, pressure. It's this core concept that explains not just why a knife cuts, but honestly, so much more about how our world works. So what exactly is pressure? Well, put simply, it's the force you apply squished into a certain area. It's not just about how hard you push, it's also about how small the spot you're pushing on is. The more you concentrate that force, the higher the pressure gets. Simple as that.
Okay, here's a perfect example. Picture someone in high heels trying to walk on soft grass or dirt. Their entire body weight, that's the force, is getting focused down onto two tiny little points. That creates an immense amount of pressure, and that's exactly why they sink right into the ground.
Now, let's flip that idea on its head and look at a camel in the desert. A camel is obviously really heavy, but look at its feet. They're super wide and flat. They act kind of like snowshoes, spreading its weight over a much larger area. This drastically reduces the pressure on the sand and lets the camel walk right over it without sinking. See the difference?
All right, so we've got the basic idea of pressure down. Now let's get a little more specific and see how we can actually measure this stuff and put some numbers to it.
So the formula is actually really simple. It's just pressure equals force divided by area. And the unit we use to measure it is called the Pascal, or PA for short. It's named after the scientist Blaise Pascal. So basically, 1 Pascal is just 1 Newton of force spread out over 1 square meter. Okay, time for a little brain teaser that really shows why this formula is so cool. Who do you think puts more pressure on the ground? A 50-kilogram person wearing stilettos or a 2,000-kilogram elephant? Think about it for a second. Ready for this? Believe it or not, it's the person in heels. And not just by a little bit. Because all their weight is focused on those 2 tiny points, they exert a whopping 12.5 times more pressure than the elephant. Isn't that wild? Our brains think bigger and heavier means more pressure, but science shows us it's all about how concentrated that force is.
And once you understand this principle, you start seeing it everywhere in engineering and design. Think about it. Building foundations are built wide to spread out the building's massive weight so it doesn't sink. Tractor tires are huge and broad to lower the pressure on the soil. And then you have the opposite, like the tip of a nail, which is sharp for one reason, to concentrate all the force from your hammer into one tiny point and drive it straight into the wood.
Okay, so we've been talking a lot about pressure with solid things, right? Stuff we can see and touch. But what about the air, the stuff that's all around us? Well, it turns out air has pressure too, and it's this incredibly powerful, invisible force that's acting on us all the time. Now, this might sound a little weird, but all the air in our atmosphere actually has weight. A lot of it. We're basically living at the bottom of a giant ocean of air, and it's constantly pushing down on us from every direction. That constant push is what we call atmospheric pressure. And you can actually see this in action with a super simple experiment. Just fill a glass with water, slide a piece of cardboard over the top, and carefully flip it upside down. And the water stays put. So why does that happen? It's because the air pressure from the outside pushing up on the cardboard is actually stronger than the weight of the water pushing down. How cool is that? Okay, so here's where it gets really interesting. That atmospheric pressure we just talked about, it's not the same everywhere on the planet. And those differences, well, that's what gives us wind. It's what shapes our weather every single day. There is one golden rule you need to remember about wind, and it's super simple. Air always moves from an area of high pressure to an area of low pressure. That's it. You can think of it like nature trying to balance things out, and that movement of air, that's what we feel as wind. So what causes these pressure differences in the first place? Well, it really all comes down to temperature. When the sun heats up the ground, the air above it gets warm, it expands, and it starts to rise. That creates an area of low pressure. Meanwhile, in colder spots, the air is denser and sinks, which creates an area of high pressure. And what did we just learn? Air always flows from high to low. Boom, you've got wind.
Here's another really cool way to see this in action. If you hang two balloons next to each other and blow a stream of air right between them, you'd think they'd fly apart, right? But nope, they actually move closer together. That's because the fast-moving air you created is a low-pressure zone. So the higher pressure air on the outside of the balloons literally pushes them in. It's a neat trick called Bernoulli's principle. All right, let's scale this whole idea up. We know that pressure differences create wind, but what happens when those differences get really, really big, like extreme? Well, that's when you can get one of nature's most powerful and destructive forces, a cyclone. So how does a cyclone get started? It all begins over warm ocean water. First, a ton of warm, moist air, that's the storm's fuel, starts rising really fast. This creates a huge area of extremely low pressure. Nature hates a vacuum, so cooler air from all around rushes in to fill that gap. And finally, the spin of the Earth gets a hold of all that moving air and whips it into a gigantic, swirling storm. And a fully formed cyclone is just immense. It's a massive system of rotating winds that can be hundreds of kilometers across. It's basically a giant heat engine made of wind and rain, all spinning around that famous, calm, low-pressure center that we call the eye of the storm. Look, understanding the science behind all this isn't just for fun, it's also super important for safety. If you live anywhere that gets cyclones, you absolutely have to be prepared. Simple things like having an emergency kit, staying tuned to official warnings, and knowing where to find a sturdy shelter, these things can literally save lives. So there you have it. We went from the tip of a knife all the way to a massive cyclone, and the one concept connecting it all was pressure. It's just a great reminder that sometimes even the smallest, most focused forces can have the biggest, most incredible impact. Now that you know what to look for, what other examples of pressure are you going to spot in the world around you?